Morning, everyone. So today we're talking about kinetic theory of gases. It's in Atkins 1B. When we were discussing ideal gases, we had these macroscopic variables: volume, pressure, temperature. Those are things that we could measure, right? Macroscopic. They're distinct from the behavior of the molecules themselves, right? The microscopic behavior. So a classic example of this is temperature. When we think about temperature, we think about how fast molecules are moving. Kinetic theory of gases is a technique that allows us to answer these types of questions that connect molecular behavior with the macroscopic variables that we actually measure. All right, to start, I need to have some definitions. So speed and velocity. Recall from your physics class that speed is a scalar. It only has a magnitude. So I'm traveling with a speed of 60 miles an hour. In contrast, velocity is a vector. It has a speed and a direction. So I'm traveling 60 miles an hour and headed east. And this distinction is important. So if you start thinking about it, you can answer some simple questions. What's the average velocity of an ensemble of gas molecules? By ensemble, I mean a collection, a distribution of gas molecules. And so you think about it, some molecules are headed left, some are headed right, some are going up, some are going down. It will turn out that all of this motion will cancel one another. Right? So motion in one direction is canceled by motion which is equal and opposite in the other direction, and the average velocity of a group of molecules is 0. What we're interested in are speeds. Right? What's the average speed of a group of molecules? And at this point, I just want to make you aware of a little quirk. Atkins uses funny notation. He uses V for speed. Right? I am going to use U for speed throughout here and V for velocity. All right, so we can start to get into it, and what I'm going to do at this point is a derivation for you. If you don't like derivations, you can skip ahead a minute or two. But kinetic theory of gases is a classic way that physical chemists solve problems. And the starting point for this is the recognition that the kinetic theory of gas model is the same thing as the ideal gas model. I'm not going to belabor the point, but we basically have molecules which are running around in random directions. And so if I were to draw a picture of it, it would look something like this. I'm still learning to work with my pen, but I have some container. It's full of gas molecules. Don't do that. Don't do that. There we go. One here. Okay, here's one here. Don't do that. Don't do that. Don't do that. Me and my pen are not getting along today. It would be funny if it weren't so sad. Oh, yeah. Hey, there we go. Okay. These are running around in random directions. Right? So some's going up, some's going down, some's going this way. Should have left good enough alone. This molecule, I'm going to imagine, is going this way. It's going to strike and hit that wall. When it hits that wall, it'll bounce off. And so what I need to do is think about the force associated with this collision. You may recall from your physics, I'm going to put in approximately equals here, that I could approximate that force as the time derivative of momentum. It's the change in momentum divided by the change in time. And momentum is mass times velocity. So I'm going to give these molecules some mass m. SOB. I cannot win here. There we go. They have some mass, m. And I'm going to imagine that this is traveling towards the wall with some velocity in the x direction called vx. So initially it's going one direction. At the end, it's going equal and opposite in the opposite direction. And this change in momentum is going to end up being 2m vx divided by delta t. I'm leaving good enough alone. All right, that's the force associated with one collision. Now what I need to do is think about how many molecules are actually going to hit the wall. And here's how you do that. The number of collisions. It's given by the total number of molecules times the percentage that are in something called the collision volume. So here's what the collision volume is. I'm changing my pointer color. My daughter just walked in the room. Trixie, you want to say hi?
Hi.
Imagine this molecule here is associated with some volume, and any molecule that's inside of that volume would hit the wall, right? That's what the collision volume is. And so I'm going to give the wall an area A. Stop. What I need to know is what this length is. And if you think about it, this length would be given by Vx delta t. Velocity times the time gives me a length. And so the collision volume then is given by length times width times height. So again, I'm going to switch my marker back. Equals n total times this collision volume, Vx delta t, that's the length, times the area, volume time. And I need to do one last thing here, which is multiply this by a factor of 1/2. That says 1/2. The reason is that some are going left, some right? So it's, again, this velocity notion. Okay. At this point, I can multiply these two quantities. So if I want the force total, I'm going to take the force of one collision times the number of collisions. Right, force total equals 2m vx delta t times 1/2 n tot vx delta t a divided by v tot. Do some cancellation. Cancel, 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 cancel. And I get an expression which looks like this. All right, that's the total force that the system experiences. Next step is I need to handle the fact that I've only worried about an X direction here, but I have a three-dimensional system. And so here's how that works. Oh, and I forgot an area in this expression. So again, using a little vector notation, you may remember that I get expressions like this. Right? That's a dot product. And if I recognize that it's isotropic, right, Vx equals Vy equals Vz, I will get an expression like this. Which I can solve for Vx squared, and I get that that's 1/3 V squared. Next thing to recognize is that in that previous expression, I had this, force equals I'm going to do two things here. Remember that pressure is force divided by area. So if I bring this expression A down here, I will get an expression for the pressure. And I'm going to substitute in this relationship for Vx. So I will get something that looks like this. N tot M. I'm now going to bring volume total over here. And I'm going to recognize that N total, the number of molecules times the mass of one molecule, can be written in terms of the number of moles. So if I rearrange some things, I get 1/3 V squared N M, where this quantity is now the molar mass. This expression, little m, was mass of one molecule. This is now per mole. PV equals this. So you might guess I can now use the ideal gas expression and set this equal to nRT. Last but not least, solving for V squared, I get 3RT over M, or my last expression, if you followed nothing else in this, put this in your notes and circle it, right? This is the important equation. This relates the speed of the molecules to the temperature, right? So a couple comments and then I'll end. You might imply or understand from this that all gas molecules are moving at a uniform speed, right? They're all going at one speed, but it's not right. That's not what this model is actually suggesting. There's some nuances to it, and that would be an incorrect interpretation. Gas molecules exhibit a distribution of speeds. What we're technically measuring here is something called the root mean square speed. And so we're going to give this the label RMS for root mean squared. Root mean squared is given by this expression. You may be wondering what this is, and what I would say is basically it's like an average, but it's not actually the average. And we'll talk about this a little bit more later. You can use this same type of analysis to calculate other quantities. So there's two we're interested in. The first is the collision frequency Z. The collision frequency is the number of collisions per unit time that a gas molecule experiences. It's given by this equation here. There's a couple new variables in here. The first is this one, sigma. Sigma is a collision cross-section. It's a tabulated quantity that describes the cross-sectional area of a molecule. You can find it in Atkins. UREL is the relative speed between gas molecules. And I've given you an equation for that here based on the RMS speed that we just calculated. And then the last but not least is this quantity K. K is actually a fundamental constant called the Boltzmann's constant. And it's given here 1.381 times 10 to the negative 23 joule per Kelvin. The other quantity that we can calculate is the mean free path. So I know how fast gas molecules are going. Give me 1 second. Okay, I'm back. Mean free path. If I know how fast molecules are going, meter per second, and I divide that by the collision frequency per second, I can figure out how far molecules are moving. Okay? So that's what the mean free path is, how far they go before they hit one another. Definitions here are all like the previous equations. One thing I would point out to you is that the equation for Atkins in this is actually incorrect. It's missing a factor of √2. So as we go through and do some problems, I'm going to expect that you can use this equation for all calculations. All right, thanks for bearing with me. I went a little long, but I will stop here and I will see you next time.